Hello, high water viewers, and welcome to today's episode where we're going to be jumping back into our review of the FE. And today's topic is going to be on open channel flow, which can be certainly a challenging topic, but we'll just focus on a few simple examples that you might actually find on the FE. Before we do that, though, I want to just take a quick moment to thank anyone who has viewed our videos or subscribed or left some comments or likes or anything they've done to join the community has really been appreciated. We really do appreciate it a lot. It helps us keep moving forward. Okay, back into open channel flow. What is open channel flow? You probably have at least a pretty intuitive idea if you're watching this video. Obviously stream flow, we have trapezoidal flow here on the left. Is an obvious example, but it also can be like a pipe half full, like with either sanitary sewer or with storm sewer management. Any of that can be open channel flow, and generally speaking, it's flow that the surface is at atmospheric pressure, or the water surface is exposed to the atmosphere. Now, that can get a little bit, maybe not exactly true when you're talking about sheet flow or shallow concentrated flow, but generally speaking, that's the definition for open channel flow. Okay, so we're going to look at a couple of simple examples. One's going to be the Manning equation for sewer design. I think really, if there's one thing I would recommend knowing for the FE, the environmental FE at least, would be the Manning equation, or certainly for open channel flow, you want to be able to be familiar with the Manning equation, because you're probably going to see that, I would expect, in some form. Another quick example we're going to work through is finding critical depth for a stream, and a little bit about what that means. All right, let's take a look at our first example here, where we are going to be examining a sewer design using the Manning equation. Sewer design for a school where we have certain criteria, one of which is that it needs to supply a 50 cubic feet per second flow rate. It will be using the material of finished concrete as the pipe material, and the pipe will have a 3-foot diameter. Now, given these characteristics, we need to find what slope will be able to provide that flow rate for this material and diameter. Now, the material is important because when you're using the Manning equation, obviously an important aspect of the flow is going to be friction, right, and lack of friction. So with a finished concrete pipe, you have a pretty smooth surface here. So I looked that up in a table online, and the K value, the roughness coefficient for a finished concrete pipe, is 0.012. If you had something like masonry, you might have like 0.02. Generally, you're going to be between 0.01 and 0.02 for most construction materials. Okay, so that is the information that's needed to solve this problem. If you are studying for the FE, I do really recommend that you give it a go here. You practice these examples. That's really going to be the best way to prepare for the FE. And so if you want to pause the video and give it a shot, I'll see you in just a moment. Okay, well, welcome back. I hope that went well for you. If you did, give it a shot. What we have here on our first equation here is the general form of the Manning equation. What we have is the flow rate Q equal to our K value, which is a correction for what type of units you're using. So if the Manning equation is empirical, you're basically fitting a line to a bunch of data. All right, so this was developed in SI units, so there is K is just 1, there's no correction there. But if you're using US units or conventional units, you need to adjust that line to fit the data, basically. So you'll be multiplying by 1.49. N is our roughness coefficient. A is the flow area. RH is the hydraulic radius to the 2/3 times slope to the 1/2. So if we rewrite that to solve for slope, we have here Qn over Ka RH to the 2/3, and then the whole thing squared. So in our example, we have S equals 50 feet cubed per second. Now it's important that your flow rate is per second, because again, this is empirical, so you need to adjust. If you're given something that's not flow rate per second, you're going to need to adjust that. Oops. Now we have our roughness coefficient 0.012. This all divided by our correction for our units, our US units. Kind of lost my thing there. Boy. Windows, sorry about this. So maybe I can edit this out. Layer editor. There we go. All right. Now times our radius. So, or of course you can use diameter, but we'll just use radius squared times pi for our area. Now, in this design, we're going to assume that our pipe is flowing full. Basically just perfectly full, right? It's not pressurized, but it is full. Oh, I'm being a little bit weird today. I spelled equation wrong. How did that happen? Equation. Okay. Goofball. All right, so we have r squared times pi. Then we have our hydraulic radius. Now, hydraulic radius, just real quick, if you're not familiar with that, it is your area of flow divided by your wetted perimeter. So in this case, a pipe full, RH for full pipe, is real simple because it turns out to be the radius divided by 2. So that's probably the simplest example of calculating hydraulic radius. And so that's what I would expect you to see on the FE, because they're not really going to want to make it really challenging or time consuming. So that's our R value to the 2/3, and this whole thing gets squared. Okay, so if you solve all that, this comes out to be 0.004, about 48. So in terms of slope, that would be about, almost 0.5, so 0.48% slope. Okay, so that is it for that one. For our second example problem, we're going to be solving for critical depth in a rectangular channel. So what we were given here is the area of our flow and the width of our channel, and basically nothing else. So from that, we can solve for our flow rate, is the first thing we're going to need to do. And then from that flow rate, we can determine what our critical depth is. And we'll talk a little bit more about critical depth once we get further to that. So for our flow rate, we have this equation: flow rate squared divided by gravity is equal to area cubed divided by top width. All right, so the water surface width. So if we rewrite that, we'll have Q is equal to, in our case, for our example, we have 27 feet squared, and this is going to be cubed divided by our width, which is 9 foot, times our gravity, 32.2 feet per second squared. Okay, and then if you work through that, you will have 265.37 feet cubed per second. All right, and then from that, we can solve what our critical depth is. So we come over here, we've got our Q rate, our flow rate that we solved in the last part of this problem. Now the formula for critical depth, I see it written a lot of different ways. I believe in the manual, in the FE handbook, I guess, I believe it's written as this little q squared over g to the 1/3, where this little q is going to be the flow rate divided by the base width, right? So in a rectangular channel, obviously the top width and base width are going to be the same. So let's go ahead and solve this. Our Q, our Q is going to be the 265.37 divided by 9 foot, and of course this is feet cubed per second, and so this is going to be 29.49 feet squared per second. And then from that we can solve for our critical depth. So we have 29.49 0.49 feet squared per second squared divided by our gravity, 32.2 feet per second squared to the 1/3. And if you solve this, you have your critical depth of 3 feet. Okay, so now that we've solved for critical depth, what does that even mean, right? And critical depth is it's kind of the exact balance between subcritical and supercritical flow. It's defined mathematically as the lowest energy point. So you have, if you were to plot this, if you were to plot different depths versus energies, you, at the very lowest energy of this curve, you're going to get this sort of parabolic curve here, and at its minimum is your critical depth. Now anything, as you have increasing energy, you actually have two possible depths for a given energy state. You have a supercritical and a subcritical depth. So as you have higher depth is actually when you have subcritical flow, and that maybe intuitively makes sense because if you have a deeper depth, you actually have less velocity. And when you have this shallow depth, you have more velocity, and that's where you have, basically you have very erosive velocities at that point. This is where you're going to have stream damage, or your sewer system is not going to last very long because of erosion and other high velocity problems. So really, if you were to do this design, you're going to want to make sure that you're staying in the subcritical zone. Well, I hope this was helpful to you if you are studying for the FE. We're going to put out a few more of these in the future, coming up pretty soon, so stay tuned. And again, a big thank you to anyone who has subscribed to the channel or left a comment or gave us a like. That's super helpful to us, so we do definitely appreciate it. All right, well, thank you, and see you next time.